Did you know that the batteries you use for your solar panels or the ones in your electric vehicles can actually be made from forest and agricultural waste like fallen tree branches or palm kernel shells? In today's episode, we'll dive into the world of green batteries made from forest waste. We'll explore how this innovative approach could revolutionize energy storage while reducing environmental impact. Stay tuned. Welcome to the Sustainability Nugget podcast. I am Rarasu Maraibi.
And I'm Tosin Faloranjo.
On this podcast, we'll learn about sustainability by discussing various related topics while focusing on three pillars: the economy, the society, and the environment. Hello guys, welcome back to the pod. Today we're going to be learning all about green batteries, and we have Ridwan on the pod today who is going to be telling us about this technology, telling us all about his research and the future prospects of green batteries. Hello Ridwan.
Hello Rosemary, how are you doing today?
I'm doing great. Thank you for accepting to be a guest on the podcast today.
It's my pleasure. Thank you for having me.
So let's just start off. Please, can you introduce yourself to the audience, your background, and what you currently do?
Yeah, my name is Ridwan Tobi Ayinla. I am from Kwara State, Nigeria. I have a bachelor's degree in physics from Ladoke University of Technology. And I moved to Malaysia for my master's degree in University of Technology Petronas, where I studied material science, the physics of material. Basically, battery materials specifically again. So after that, I discovered that we cannot fully explore the advantages of battery materials, especially from sustainable product, without understanding the fundamental of chemistry of these materials. So I moved to Mississippi State University, Department of Chemistry. I picked another Mississippi State University. So to pick another master's degree in chemistry. So in that place, I was studying also materials, this time the chemistry of materials, and I was also studying some scanning probe microscopy as it's applied to different type of molecular chemistry. So after that, since my primary objective was to understand sustainable materials, now I am in Ph.D. program of Mississippi State University in the Sustainable Bioproduct Department, where I focus on the development of green batteries and supercapacitors, basically from sustainable products.
So now you're doing your PhD, and like you said, you're working on green batteries, like sustainable materials. I know you've already said without batteries definitely for energy, but I want us to just even start off what is the traditional batteries, what are they before we even come into the green batteries that you say you're now working on? What's the use? What are the materials being what is the current state of technology, the common batteries being used, and what is the applications for all of these batteries before we jump into green batteries?
Thank you so much for wanting to know about my research. So the background of this research area is basically we are trying to optimize, store, and distribute energy efficiently, because we know that energy is like a fundamental thing that we all should have access to. So, and then if we don't have batteries to store this energy, it's a problem. Because take, for example, if the world is now talking about renewable energy transition initiatives, for example, the United States is taking the lead on that. However, if we focus on, say, solar energy as an example, if we have sunlight coming out a lot, like the intensity of the sun is coming out a lot in, say, Louisiana or Mississippi in the summer, but in Alaska it's different. So we want to take advantage of what we have here in Mississippi State. We want to be able to harness this energy. We want to be able to store it. We want to be able to distribute it effectively in such a way that everybody can have a share of what is happening. Because in fact, in Alaska, it's all around cold. We don't have too much luminescence from the sun all around the year. So also if we think about the hydro power that we generate, not everywhere has the water bank in their bay, or like San Francisco and some other areas, right? Or say Florida. So for example, in states like maybe Texas, they have very little water, or some states in the middle of the country. So we want to be able to store this energy from the coast and bring it to the center where people can have access to it. So it then makes battery a formidable or a very key complementary device for effective power or say energy delivery. So, and as you ask in the beginning, people were talking about fuel cell in the beginning of all of this energy storage. It was fuel cell, but there was a problem with fuel cells. Fuel cell have very high energy density, but the power density is very low. So what do I mean by energy density? The capacity of a material of a device to store a high amount of energy is what we mean by energy density. But the power density is the ability of that device to dissipate that energy when we need it. You have stored a lot of energy, but we need you to dissipate it when we need it. That's the power density. So it's very, very low. So that's why people say, okay, we cannot continue to rely on this, because what's the point storing a lot of energy, then you cannot have access to it when you need it. So on the contrary, then people began to work on an alternative. Then they developed batteries. And batteries, as you may have known, have high power density, but the energy density is very low. Batteries can give you your energy when you need it, but the energy density is very low. So it's like a trade-off.
So the energy they store?
Yeah.
Okay.
The energy battery store is very low. Take for example the EV, the electric vehicles that we use. The market is dropping so fast because of the batteries. People think the batteries
So
are
when you say,
unreliable.
sorry to cut you, but like when you say low, like what percentage? Because like what from what you explained and what I'm thinking about, energy density is how much they can like collect. Then power density is how much they can dissipate. So when you say low in relation to the amount of power or energy that's coming in, what's the percentage that the current batteries can store?
That's a good question. However, I may not be able to put a figure to it because
Yeah.
we
Okay.
have different type of materials and different type of batteries. So if we want to really talk about the figures, we need to put things into perspective. Like, are we talking about sodium ion batteries? Are we talking about lithium ion batteries? Are you talking about carbonaceous compounds, supercapacitors? It's a lot, different type of material that people are trying to explore. So I cannot say, okay, except we are saying, okay, for example, this particular version and stuff, and even the fabrication, how we make the batteries also affect everything. So it's a lot going on in the battery industry right now. So, I mean, it's hard to put a figure to it. But in general, it's in general, we say it's low because we expect higher than what the system actually needs. For example, if the system needs 100% and we are seeing 40% delivery, then it's low.
So, but like, can you tell me? I know, like you say, you can't put a number, right? But like, maybe in the best case scenario, what's being seen now in the industry? Like you said, maybe we need 100%, but we're seeing 40%. Like, just to have a sense, because I want to know, like, where is the direction of the research going to improve? Like,
for example, the dominant material in the field right now is lithium, and that's why you keep hearing lithium ion battery. I'll make that as an example, right? So and so far it's delivering the highest amount of energy density that we have seen. But to be honest, in the scope of things, say when we need a system to optimize at 100%, say we are able to generate like between 65 and 70, and that's still relatively low. Low. So it requires recharging and all of that. And then we see we need to conduct life cycle assessment. How much charge and discharge can we run on a battery before it finally collapses, and all of that. So the longevity, the durability, the material degradation, and all of that. So all of this play a role in the system.
So yeah, thank you for like putting that base, like for us to know what's currently out there. I know like you just like mentioned it briefly. We don't need to go deep unless you're like maybe picking one and that's very related to your research, but you mentioned like the lithium ion, the supercapacitors and some other ones. So now that you're working on batteries still, but green batteries, what is like the motivation to actually look for the alternative? I know you've stated like energy density, but like in like telling us an awesome motivation why this alternative, why you're like pursuing this alternative and how it can be better than the current state of technology.
So green battery and supercapacitors are very, very important and key for sustainability. Why am
Mm.
I saying this? Sustainability is our ability to say harness our needs now without compromising the ability of the future generation to also access the same advantage that we have. So if we can take care of
Mhm.
today without compromising the future, we say that system is sustainable. However, when we look at
Mhm.
the key or say the overall landscape of what is being done today in the battery and the innovations that we are seeing, bulk of what we do today is based on lithium, right? And lithium, as you may have known, is a finite element and it's being mined all around the country. And this mining causes a lot of environmental degradation. It's just like you're mining the crude oil or something. And then it is finite. Sometimes we might just say, okay, the crude oil, the lithium is going down and is exhaustive. It's no more. So we need to be able to take into account these things and be able to provide a more environmentally friendly material in terms of environmental degradation caused by mining, in terms of the carbon footprint that we put out there, also in terms of sustainability. So if you ask me, I would say the future of battery is in our ability to be able to generate or make a sustainable material our precursor for making whatever
Mm.
battery we are doing, or say supercapacitors. So to a very large extent, my key drive is about the future generation. What if lithium is finished tomorrow? What if everything got exhausted? What's going to happen? How are we going to continue? So that's the main drive. That's the main drive. And I think this drive aligns many other key stakeholders and government parastatals, aligns us on the same page. For example, the DOE is so particular about the sustainability of energy storage devices. Also, because we are using sustainable products like forest waste and stuff, the USDA is also very much interested about what we are doing. Because if we are able to convert our waste to a value-added product, that's a big deal, and that's my major drive.
So please, before we go further, can you just give us the difference between batteries and supercapacitors? Are they not this? Are they the same or what are they?
They're not exactly the same. That was what I was trying to drive at when I was explaining energy density, power density. So I talk about fuel cell, that fuel cell have high energy density, but the power density is low. Battery, on the other hand, have high power density, but energy density is low. Supercapacitors, on the other side, straddles between fuel cell and supercapacitors. They can dissipate their energy very fast, and they have relatively high energy density as well. So they are in between both. But if you have a graph that is showing, let's say this is power density, energy density. So we have the fuel cell here because it has high energy density, but the power density is low. So the battery has high energy
Mm.
density, power density is low. So we need something that is going to straddle both sides, that take care of the power density and energy density. And those are supercapacitors. And they are doing fine in the industry today. Many of them are being commercialized. I don't know if that answers your question.
Okay.
Yeah.
So yeah, I get that there's in between, but I'm actually trying to picture it, which I'll go and look for the picture after this. For batteries, I see it as like storing fuel cells. I thought was like for what I knew about fuel cells. I know they use it to like generate energy, not really store. Like like it used to work like turbine, or maybe I'm wrong. But like I thought like some I felt like fuel cells were used to like maybe generate electricity, not basically store it. Do you know of like fuel cells that use like natural gas or like landfill gas to produce electricity? Is
So,
that how it
so
works?
fuel cells, so fuel cells,
Yeah.
batteries, supercapacitors, all of them are energy
Yeah.
storage devices. All of them.
Oh, yeah.
They are
Okay.
all energy storage
Okay.
devices. So it's in three
Yeah.
stages. There are people who work on energy capture, be it solar, wind, hydro, whatever. They work on energy
Mm-hmm.
capture, but when they capture this energy, or say energy conversion, So, but when they convert this energy, if it is not for immediate use, we need somewhere to store this energy. So that's what fuel cell does. That's what battery does. That's what supercapacitors does. It is just mainly to store energy.
Okay. When we're now looking at like the green batteries now, what are like the common raw materials that is used like in producing so-called green batteries? And wait, first of all, before you even answer that, when I hear green batteries, I'm just hearing a sustainable alternative to batteries. It can be like a wide range, right? Because on this channel, I interviewed a guest that we talked about sand batteries. Do you think sand batteries fall under green batteries since this, I don't know, that's
Sand
sand
battery.
though, but I'm just saying like it's sand. So it's not like being mined. I don't know if that falls under green batteries. But like when we talk about green batteries, what are like the common raw materials that are being used in producing these green batteries?
Okay, good. That's a very important question to the field. So when we talk about green batteries, like I said, we are looking at sustainability. We are looking at reducing the carbon footprint out there. So our major precursor are forest waste, like forest product, landfills. These are our major precursor. But we have series of thermochemical processes, physical processes that we go through, we make these materials go through to convert them into the actual material that we desire. So we are particularly interested in the chemistry of these materials, the physiochemical properties, the electrochemical properties, because at the end it's about electron moving around. So we want materials that are very good. So, but the precursor is what we have first. When we have the precursor, we cannot use it like that. We need to convert them into what we want. So then the old physics and chemistry come into play. So we talk about the thermochemical processes that I talked about, different temperature and different stuffs going on in there. We talk about functionalization. We can put with chemistry. I mean, everything happens with chemistry. The behavior of anything, anything at all, anything. The behavior of that material depends on the chemistry. With good chemistry, we can play around many things. We can take them into nanoscale and make them behave the way we want. We can put some other add atoms, molecules on the faces and make a lot of different type of functional groups that we want on the surface. And then we have different avalanche of material that we can explore. We can use any forest product at all. We have the capability to test the chemistry of that product. We have the capability to tune the properties of that product. We have the capability to tune what we get out of it into nanoscale. We have the capability to check what we can adjust to make it better, right? So with good chemistry, I mean, we can do a lot.
Yeah. So I want to know, like, in your own research, what are your, I know you said forest waste, but like what waste, what particular waste? See, palm
Good.
kernel. I don't know if I saw palm kernel somewhere. That's in my, like, did you use
Yeah,
palm
so when I
kernel?
was in Malaysia, the major plant that they grow in that place is palm. They have a lot of palm. And the active milling of palm, because they mill a lot of palm, they generate a lot of palm waste. So when I got there, I was looking for the opportunity to be able to convert this waste into value-added products that will be useful. So that was why I worked on palm kernel waste at that time. Interestingly, we were able to do a lot with that. So for example, the waste from palm milling, we have PKS, which is palm kernel shell. We have OPF, which is the oil palm frond. We have EFB, which is the empty fruit bunch. A lot of waste come out of that place. So what I did was I first took this material. We do the lignocellulose chemistry, because any plant that you see, the major component of this plant is lignin, cellulose, hemicellulose, extractives. So we did the lignocellulose chemistry of this waste. I don't want to bother you with too much chemistry. Okay, so we did the lignocellulose chemistry of this material, and we observed that they have different composition. But what we desire to be the base material of our in our system is also different. So we kind of extracted what we need from this part, and extracted what we need from this part, and then use some complementary chemistry to bring them together so that they can work together. So we kind of call it, because the lignin in one is higher than another, cellulose in one is higher than another, like that. So we kind of call it a complementary chemistry because we were complementary from the same nature product. We did that and we were able to achieve a very key significant landmark with some of our product were prototype in Malaysia. That's at the lab scale though. So before I moved to the United States. So to answer your question straight, we can pick any forest product, even animal bones and whatever, anything at all. So because at the end, we need to see what is the chemistry of this material and what is useful in this, because we can go into the smallest molecule. We can check what is the chemistry here, what's happening here, what is in this, what is this used for. We can see the functional group, if we are seeing an hydroxyl group, if we are seeing a carboxylic group, if we are seeing anything, if it's an aldehyde, ketone, we know what they are used for. We know what they are good for in the system. So we can easily take them out and use them to make something else. So it's about the chemistry. We don't care where the product is coming from. We don't care what we care about is, are we able to see chemistry of this material? If yes, then we are good. So the other things is just our own expertise to make things work.
Yeah. So, but when you say that, like, for example, in the biogas world, like when you just do anaerobic digestion and all, we want to avoid high lignin products. So woody products and all, like, do not digest easily. Like they get, so like we kind of like want to avoid that. But from what I'm hearing, like you guys want like materials with that lignocellulose, like with high like lignin, high cellulosic materials, right? But when you say that like, you can extract whatever, if you go far from like the components you're needing, does that not now like add like cost and all to the whole process? So when you're saying like you can get everything in your extraction period and whatever, the further the component of of the raw material to what you want, doesn't that like impute cost to the process? You get what I'm saying? I'm just trying, like what I'm trying to find is that are they not like more feedstock or raw materials that are desired, like more desirable feedstock than others?
Good. That's a good question. So let's go a little bit deep into the science because this requires a little bit of explanation. So in supercapacitors and batteries, we have majorly three types. We have one that we call EDLC, which is the electric double layer capacitor. EDLC, electric double layer. There's another one called the pseudocapacitor. And then the third one is the hybrid. The hybrid means it's using both, right? Both EDLC and pseudocapacitor. So how do we do this categorization? We do this categorization based on the material that we use to make the battery or the supercapacitor. Based on the material that we are using to make this supercapacitor, that's what informs this categorization. If it is EDLC, it means the material in there is a carbonaceous compound. They are carbonaceous compound. Any carbonaceous compound we call them EDLC. And it is EDLC because when we make the supercapacitors, they have two capacitors facing each other like in parallel. And then we have electrolyte in the media, and they can store charges on the surface of both capacitors. That's why we call them double layer capacitor. You see what I mean? That's why we call them double layer capacitor. Now, whatever feedstock you have, coming back to your question, whatever you have at all, anything, whatever it is, you can carbonize it.
Okay.
You can carbonize it. So you hardly go wrong on that, except you don't know how to make it. You can carbonize it. So if you can carbonize it, then it means you can easily make an EDLC out of anything. Now, if we check the base material of a feedstock and we see that it has some more useful polymeric compounds, instead of EDLC, that the base material, or say the active precursor are carbon, or say carbonaceous compounds, for pseudocapacitor is metal oxides or conductive polymers. Polymers that are conductive or metal oxides. So these ones store materials using redox reaction. Instead of storing the charge on the surface like EDLC, they use redox. So you may have known that some metals can undergo redox reaction, even up to like 3. We can have different type of redox stating where you can oxidize and reduce them. So they have this dual phase. So when you oxidize, it may be the charge state. When you reduce it, it may be the discharge state. You see what I mean? So if we see that
Yeah.
the material that we have a high or say useful metals or very nice conductive polymers, what we do is we extract them and use them on the other way, you see.
Okay.
So you
Yeah.
cannot go wrong
Makes sense.
on this chemistry.
Yeah.
So I'm sorry I
Yeah.
need to take you a little bit deep to be able to
No.
understand
Thank
this
you.
part.
Yeah.
Yeah.
Thank you. That actually makes sense. So I know you said when you're in Malaysia, like you guys are like at the lab scale pilots, but like this type of technology, is there like anywhere in the world where it's already being done like in scale, like out of the lab per se? That's what I'm asking. Like, is
Yeah.
it
A lot.
being?
Singapore has it. In the US, it's there in the market. We have
Mhm.
supercapacitors that are made from carbonaceous compound. Even if you pick a normal battery that you have, if you open it up, everything you see in there is black. Those are carbons. Those are carbons.
Mhm.
Those are layers of carbons. If you ever open a battery,
Yeah.
everything is those are layers of carbons.
Yeah.
It's just what you have outside there. But the base material of what they are making them from is what is different.
Is what is different. Okay. But it's
Yeah.
very, you've been interchanging supercapacitors and batteries, but I get that. But like this is different from lithium. Like, because when you're saying precursors, I get in the carbonaceous, whatever is used to now do those carbonaceous material. But when we talk of lithium ion, is there any carbonaceous stuff there?
Good.
I want
So
to be clear.
lithium is a metal. Like I explained, those ones
Yeah.
are different from that's why I explained the operational principle of both on both sides. If it's carbon, what we want the carbon to do is to have high surface area because we'll be storing charges on the surface. For lithium ion, it's different because that's a metal. That's a metal. They don't follow the
So how
same
does the
operational
performance?
principle.
Oh,
Of course, the
okay, I
performance of
get that.
lithium ion is way better than that of carbon today. Yeah, of course.
Yeah. So the goal would be to be better than lithium, right? Or is that not the goal?
Yeah, the goal is number one, we are trying to make a cheaper complementary alternative. We are not trying to push entirely lithium out of the market. That's not the goal.
Yeah.
But we are looking at the complementary hybrid where we have a safe device because safety is also an issue. So the tolerance of carbon is way higher than that of lithium. So we are looking at safety. We are looking at the market value, the price. We are also looking at sustainability. So all of these play a role. We are looking at environmental issues that are surrounding the mining of lithium as well. So, but if we look at all of these precursors that we're talking about, they are in fact waste. They are waste products. So, I mean, we cannot go wrong on this if we get it right. We cannot go wrong on it. But in the field generally, we don't like to say or to criticize lithium. For now, that's what is in vogue. So we always like to use language complement. So not to say lithium is out of the way, no.
So, but when you compare, I get lithium is another, but when you compare with like the current carbonaceous, let me put it like that, batteries or supercapacitors that are in the market, how does the green batteries, the one with the waste precursors, how does it compare in terms of performance and even like cost? Is it on par with the current one, or is it better?
Yeah, it depends on who is making it and your expertise. Because like I said, the whole things that play out is beyond just that electrode material. We have electrodes, we have electrolytes, we have current collectors, we have separators. It's a lot going on in a battery. It's a lot going on. In fact, we are even talking about solid state. We are talking about solid state batteries now. So it's a lot going on. If you see some phones sparking light and all of that, like exploding, everything starts from the battery. It's talking about safety. So everything starts from the battery. If you see all this, they tell you don't charge your phone while making a call and all of that. There's also thermal stability issue. So it's a lot of things happening in there. So these are different research areas people are looking into. So And I would tell you today, bulk of what people are doing, to be honest, is trade-off. When you trade off high energy density, you want to make solid state, maybe the thermal stability is very low. It's really, really very low. And you cannot exceed certain temperature. But people, end users, sometimes doesn't know these things. And then they go beyond and then the phone explode or there's a problem. There's a recent fire issue in, is it South Korea? Where they are making batteries, and just like last week, and everything got fired. The whole factory got bombed, like 23 people died or so. So it's a lot going on in the battery industry. I cannot say like a figure to, because it's a lot. We are all in the characterization stage, putting things together and trying a lot of different bunch of stuff. Yeah. So
yeah. I know we've talked about like the advantages and all, but what are the main challenges you think you you face in your research and in this like area of research generally? And how you guys
so the
to overcome
main
them?
that's another very good question. The main issue with this field is standard. Like I said, like you are asking me, what is the advantage of this over that, blah blah blah. It's hard to have a base standard, a reference, because everybody is also in stuff. We don't know what is out there and what is not. That's one. Number two is, let me come to the lab. That's in the bigger picture. In the lab, sometimes when we desire a material, the chemistry are really, really hard when we go to the nanoscale, because these materials are really, really hard to control in the nanoscale. And we need to get them to that point to be able to functionalize them, to be able to treat them the way we want. But before we can be able to get to that, to make them behave in a certain way, the chemistry and all of that at the nanoscale is really, really challenging. Like, for example, you're in the lab, you document all your protocol, you have something work today, and then you come back in the next 2 weeks and it's all like a mirage, and you'll be like, I did this last week, it worked, and it's not going to work again. And you spend another 6 months trying to fix something really small. And it's just because they're in the nanoscale. They behave so differently in the nanoscale. So this is also a big challenge that I would say is,
Okay. Thank you for that. But looking forward, like if like these challenges can be overcome and like it's being scaled up, like what are the most common applications you think these green batteries can act in terms of, is it for solar, is it for cars,
Yes. So I'm really, really, really looking forward to electric vehicles, to be honest. I'm really, really looking for that. Looking forward to that. Also, I'm looking forward to, because it's devastating to know that the electric vehicles are declining, the purchase is coming down. And the whole idea, as fascinating as that product is, the whole idea of this declination that we see is behind the battery. And it's so hard to take that I'm a researcher in this field, and we are still at that stage where we give the industry complaints like we are still fixing this, we are still fixing that. So I really, really wish we can overcome all of the issues or the challenges that we have now and be able to get the industry to that point where they want to be. Also, solar energy delivery, like I talked about, the environmental benefit that we have is not equal all around the world. For example, in some countries it's all sunny throughout the year. In some places it's all cold. I made mention of Alaska. I want to be able to see a very stable energy delivery system using all of this product that we have mentioned in such a way that we will not have issues with the delivery. Also, we also have our cell phones. Cell phones are emerging. Their own problem is not even too much of energy density. They are even looking at more miniaturization. Industries are coming. They want it to get smaller. They want smaller batteries with higher efficiencies. They are pressing our neck, and it's a lot. It's a lot. They want smaller because everybody wants a very smartphone, very sleek device. So they want very small device. And if you look at the phone, the battery takes like maybe 35% of the entire device. Only the battery takes like 35% of the entire device if you look at the phone. So the industry is also asking for make more miniaturized device. They want sleeker device, and they want high efficiency. So you see, they are pushing us to the limits every other year to deliver on all of this product. And as a
Yeah.
researcher in this area, I feel responsible for that. And I hope and I wish that one day we are gonna be there. We are gonna arrive at that point.
Yeah. There's a question I didn't ask. I know we're already at the end, but I just want to quickly ask it. Does this improve the recyclability of batteries at the end of the day, like at the end of life? Having these green batteries? But you guys got
Honestly, I didn't think about this, but I know that
Okay.
there are some companies I heard of that are doing some, but it's not this type of batteries. They are doing some
Oh,
recycling in Indianapolis. I forgot the name, but
okay.
I never really looked at that. I don't want to say what I'm not quite sure about.
Yeah,
Yeah.
because I know there's like batteries recycling. Even like while I was, I just finished my PhD, going into the job market. There was a job that was meant to be batteries, but I didn't go for that anyways. But that's why I know like they are actively working on recycling batteries. But
Mm.
that's okay. Yeah. So to end off, anyone can you give like advice to anyone that's interested in this field, just how they can start or how they can get involved based on your experience so far?
Yeah, to be honest, the field is interesting. I enjoy doing what I'm doing right now. I like being in tasking environment and I like challenges. I like to solve problems. And as you may have known from this conversation, the problems are a lot that we're trying to solve. Like I mentioned, thermal stability, energy density, miniaturization, solid state devising, and all of that. It's a lot. It's a lot. So the work that we are doing today is based on the previous effort of the previous researchers. We are actively looking for young and talented scholars, enthusiastic minds that can build on whatever we are doing now, that can collaborate. I also want to mention that collaborative effort is very key. Like I mentioned, I had a physics background. Now I'm doing chemistry. I have done chemistry before. Now I'm also doing sustainable bioproducts. So it's a lot going on. So all of these expertise put together and collaboration. I want to encourage young scholars to open and not just focus on an area, to be able to diversify. So if they talk about how electron moves and all of that circuit theory, I can talk about it. If they talk about the chemistry of material, what's going on in there, I can say something about it. And if we talk about sustainability and how we can take care of the future and all of that, the greenery, that's what I'm doing now. So, I mean, putting all these things together is very important going forward. So don't stay in one place and expect that everything. So we want to put all this problem into perspective and be able to go all around and be able to fix the problem that we have. So I am calling on all young scholars out there. There are avalanche of opportunities to explore. You will enjoy it. It's fun. I like to see scientific problem, to be honest. I like to see it. I like to think about it. I like to say, okay, because of my effort, this has gone from this to this. So we are here before, now we are doing this. So, it will be good if we have more people joining the scheme of things.
Awesome. Thank you so much, Ridwan, for taking out the time and like introducing us to this technology. I've learned a lot. I know this option exists. And my audience thanks you too because they're getting to hear about this. So to the audience, thank you. If you're still listening or watching up on this to this time, thank you very much. If you're not yet subscribed, remember to subscribe to our YouTube channel or follow us on any podcast listening platform. I'll be leaving Ridwan's details, his LinkedIn, down in the description. So if you need to reach out to him, you can reach out to him through LinkedIn to discuss further. And until our next episode, continue to live consciously. And I'll see you guys. Bye. Thanks so much for listening to the Sustainability Nuggets podcast. I am Rarsu Maribi.
And I am Tosin Folorunsho. If you enjoy this podcast, please leave a rating and review on wherever you listen to your podcast.
You can also show your support by signing up for a small donation to help sustain future episodes. You can find all relevant links in the description. See you in our next episode.